It was too short. Yeah. It's like a
Like the 45 lane. We say it's forgetting about Laura. Sorry. Sorry, I didn't see it.
Maybe some catch now. Isn't that a bus cut or not many of us?
Okay.
Yeah.
Variety. Anyone else? People can come.
It's not like. It's so practical.
Here's the thing.
Yeah.
We'll just walk that money off one day. Like the whole class. Like kind of and then I'll be coffee there and then I'll I don't know, get to go to a bank for me or something. Right. Okay. Get ready to be recording this stuff. I don't act like you've been ranting. I believe you. Yeah. So the classic walk slowly and in the last 5 seconds it's sprint.
And we actually were up on our captain. Yeah, we were walking and then we ran up like this.
Right, hello everyone. Yeah. It's a long time. Right. Why are you so happy? So being yes, been hard Friday. Yeah. Right, you get out your Trig Graphs notes. Trig Graphs notes out. Hello, Nene. Okay, loads of here. Okay. Right. Right. Okay, so let's have a look. Okay, so yesterday we started Trig Graphs. Please get the notes out. Okay, if you've lost them, let me know. I'll give you a clear one. Okay.
How are we doing in August, sir?
What am I doing? Oh, I'm being a good son. That's what I'm doing.
Where are you going?
I'm taking my mama. Okay. We have not been away since COVID to the Kruger Park. Sorry? I'm just going to Croatia. Well, so I'd rather be going to Croatia. Okay. Yeah. All right.
I'm going to go to Perfume for my grandparents' 80th.
And you get to the Bible?
Sorry,
Okay, all right.
I don't know, something.
Okay, guys. We'll get to go. I know you're tired, but you know, math, relentless. Okay. Yeah. Yes, I promise you I'll give you a 5 minutes. Right, you are my timer. Right, 25 minutes, Pomodoro. Let's go. Right, you ready? But
So you're not going to get us a baseline.
right. Okay, yes, but I'm going to start adding time if people don't be quiet. Right, okay. So, guys, if you've got a trig graph, okay, first of all, what goes into the function? Think of those machines grade 8. Angles go in and ratios go out. So, in the trig graph, your x coordinates are angles, right? Okay, they must be in the green. Your y coordinates are the ratio that comes out of the function. Fish? Okay. On the Cartesian plane, we measure the angle. That's like with a protractor kind of thing. You go, poodle? Yes, poodle. Right. Okay. So, don't worry. Okay. Now, why is this frozen? Because I'm an idiot. Right, okay. Wow, look at that. Okay, and that. Okay. Right, so we're going to sketch using our your calculator, your table mode, right? Okay, for sine and cos graph. Okay, right, let's go. Mode table. The procedure for cos and sine are exactly the same. So, right, so you're gonna go. Mode what? Table. Okay. What's the start? Come on, let's do this. What's the start? 0. In this case, the end is 360. Remember, they always give you the domain of a trig graph because they go on forever. Don't try to do 2 at once, it gets too confusing. Okay, so enter f of x. If step is 90, yes. Unless there's a period change, which we'll do just now. Okay. Right, come on. Okay. So your step is 90, right? Okay. Right, try draw it. Remember, it's a smooth graph. It flattens out towards 2 inches. What's the number?
So we should ask that really well said. That's the celebrity guide.
Madam.
I've just checked out.
Ask amateur. Okay, right. So I get on your calculator it should come up 0.1 as your first point, does it? Then 90, 0, then 180, -1, 270, 0, 361. Okay, and as you can see, so you end up with this graph. Now, when you draw these graphs, they flatten out at the top and they get steeper through the x-axis. Okay, and then they flatten out like that. Okay. Right. So while we've just got one graph, okay. Don't worry. Right, go draw the next one. It's Robin. Not everyone can be like me. So for the next one, all the y coordinates are times by 4, right? So instead of being 1, 1 times 4 is 4. 4 times 4 is 0. -1 times 4. That's 0. That's 4. Right, so there are your points. And there's your graph. Yeah, both. Right. Okay, go try answer the questions about that. Inflect at the x-axis, and then they get closer towards the asymptotes.
About 9 kilometers any other.
We calculated error.
Yeah.
So you draw those in with a dotted line, and you label it. The one would be x is 90, the one would be x is 7. What are you doing? You've got anger issues. Listen, while Robin writes. Oh, it's like me writing. Right. Okay, I'll wait.
Let me try writing. You can listen to this very hard. It curves, it shows the six that comes from it goes into a street. It's just a six that goes into a street. It's just a look at your life. It's just, it's gonna be right on. More
Negative, eh?
90 and there we go. Let those unit. Oh, I'm gonna read the legal sheet. I have to measure out. Robert, I think you've got rates on this. Oh, shit. Very possible. It's just been so much. I really do say that. Otherwise, no, I don't try actually. I really we didn't.
Take your first answer. Okay, so the amplitude of F, this distance of displacement, is always equal to 1. For G, remember that's the kind of the amount of energy you put into the rope. So that's equal to 4. That's your amplitude over here. Remember, amplitude can't be negative. The domain they always give you in the question. So X goes from 0 to 360. And for the red graph, what are all your Y values? Okay, well, the smallest Y value is at that point 180 negative 1. So the smallest Y value is negative 1, but the biggest Y value is 1, and there are no gaps in the middle, right? So this is interval notation, and the range of the red graph goes from negative 1 to 1, and the blue graph goes from negative 4 to 2. Okay. Right, you've done questions like this in algebra and algebraic graphs. So go try answer those next few questions quickly. Oh, what else?
There's another. Oh, yeah, I see over. Yeah, it's bigger. It's bigger than 0. So how does X is bigger than or equal to? I know, but X, I don't know. I
don't know if this is like kind of weird, but I have this weird feeling. I've been to your house, Sophie. Have I been to your house ever? Because last night, like in the background, I was like,
Okay, so you have to describe it now. We know. You just
maybe I stole something. I don't know. Maybe- no, man, parents' evening. So I was online. Okay.
My house is 101 West of Drive, Park View. Yeah.
Wasn't much there. I didn't like anything really. All right. So first of all, are we working with a red graph or the blue graph on my diagram? F of X is the red graph. So the question is saying, when are the Y coordinates of the red graph bigger than or equal to 0? In other words, where are your Y coordinates? Positive. So if you want highlights on the graph where that happens, there the Y coordinates are positive, and there the Y coordinates are positive, right? But they want to know the X values which that happens. So if you want, then go to your answer on the number line. And on the number line, I've got from here outward, well, to naught, between here and here. It doesn't go on forever, remember? It stops. It's only drawing between 0 and 90. So, first of all, listen to the K. Can I include this endpoint over here? Yes, I can, because it's bigger than or equal to, and I can include that point. So that's your first region. Okay, where f of x is bigger than 0. So how are you going to write that down? X goes from what? What's this region? Between 0 and 90. So your first region is X is an element of 0 to 90. Okay, or there's another region. Okay, and the other region is over here, right? Or from 270 to 360. Are you happy with that? Yeah.
So if it wasn't smaller than the brackets are several.
Yeah, it would be a bit weird because if it was just bigger than, you would still include this point because at naught it is bigger than, but you wouldn't include 90. Okay, and then you wouldn't include 270, but you would include 360. Okay.
Oh yes.
Yeah. Right, what does increasing mean? It's got a what kind of gradient? Left to right up, positive gradient. Good. Okay, so highlight where that happens with another color. Now be careful. Listen. A graph is not increasing at a turning point. It is stationary. The gradient there is 0. So you cannot include where the graph turns as part of the increasing. Open Brown? Yes. So in this nice shade of poo brown, there we have where it's existing. Okay. But I cannot include 180 or at these points, the gradient is flat, right? So there is your answer on the number line. So tell me how I'm going to write that. Good. Well done. I found myself. Okay. You good with that? Is that all right? It's riveted. You riveted. It's just amazing. Okay. Right. So you got that?
Yes, tomorrow, Wednesday.
Okay. Do parents still ask you when you go home, what did your parents still say, what did you learn at school today?
Yes.
Do they really?
Yes.
You tell them.
I
I told you to actually check your comments system one. I did right last time. For my term one comment, for Taylor's term one comment, tutor comments, I congratulated her on her life science distinction. She doesn't even do life sciences. Yes.
She's a great debater. We're so Ashley.
I don't know if I felt a great spot there. Okay, have you all got this? Can I move on? Can I move on? Sorry? Can I move on? Okay, right. Okay, tan graphs. Now, there's one big difference. Listen, with tan graphs, this is a key idea. When sketching tan graphs, Robin, when sketching tan graph, using your table function, your step is 45, not 90. Okay, so your step is 45. Sine and cos, your step is going to be 90. A significant point happens every 90 in sine and cos, but for tan only every 45. Okay, so let's go straight to your table mode, right? Okay, so for mode table tan of x, right? Start is 0, end is 360, but now your step is 45. Go see what happens. If there's an error, what does that mean?
It's
Right, so listen, put your pens down for 1 second. Pen down, calculators down, just look carefully. Okay, when you use your table mode, you're going to get 0, 0, you're going to get 90 degrees, and then it's going to say error. That means there's going to be a vertical asymptote there. Okay, one little thing just to show you. On the Cartesian plane, what do I do with 90 degrees? I measure it, right? So it's 90 degrees. I've traveled through 90 degrees, I'm over here. If I take a point on this axis, over here on 90 degrees, what's the definition of tan? Shade your rear, why? Because x raised tan your. So at 90 degrees, what's the x coordinate at this point? 0, right? 0, whatever. Okay, and if you divide by 0, what happens? Undefined. Tan of 90 does not exist for that reason, right? Okay, so it's going to be a vertical asymptote. Okay, so when you see error, it means there's a vertical asymptote there. You draw it in with a dotted line, and you label the equation as x is equal to 90 degrees. That's your equation of your vertical asymptote. Robin, Pomodoro, Robin, we're in a Pomodoro. You're going to have time to talk about these things.
Pomodoro.
Sounds like a pasta.
There is a Pomodoro pasta. Pomodoro is the type of Italian tomato. So when they say it's a Pomodoro tomato, what they're saying is it's a tomato. Pomodoro means Italian. Pomodoro means tomato in Italian. Yes. Right. So you get a vertical asymptote at 90. Right, so then you should get errors at 90 and 270. Why? Just also at 270 is over here, if you're interested. And tan of the x coordinate there is also 0. That's why tan of 270 is something over 0, which is also undefined. Okay, and Taylor, what are our points? 0, 0. Yeah. And right. So this point over here, sorry, on your tan graph, always label what goes with 45. Okay. So here, this is going to be labeled 45, 1. I want that point. That's going to be how you tell the difference between the graph of tan and the graph of 2 tan or half tan or something like that. Okay. So this part of the graph does this. Okay. Y relates to this graph. Well, at 89 degrees, the x coordinate would be very small. It would be like 0.00001. And if you got something divided by 0.001, you get a massive number. Okay. These show that it's going towards the asymptote. Don't start doing some loopy loop back there. Okay. Then you get 135 negative 1, 180 naught, and 225 1. So when you draw those, you do not go draw a straight line through those points. Okay. You have to show it's going towards the vertical asymptote. Then it starts to inflect and it changes concavity at 180. Yeah, goes from concave down to concave up. Okay. Right. Big word, right? And then you get 315 negative 1. And 360 naught. So here it does that. Okay.
Yeah, you could have sheets.
Yeah.
With their H.
Okay, now you've got to draw 2 tan, and there's only going to be one difference. And this is why we label 45. Go see what happens if you enter 2 tan. There's only going to be one difference, really. Well, more than one, but it's really difficult to actually see it. Okay, yeah. What?
I'm just asking, would it give you the same answer?
I don't know what you're really talking about, so I'm just going to say no. Okay, no. But I've got things to do. Right, okay. So here you're going to have to label 45. What goes with 45 on the other graph? 45 2. You're changing the original y coordinate by 2, right? So that's going to be your only real difference. And if you didn't have those 2 points labeled, you can't really tell that there's a difference.
I mean,
You can, but it's not like as obvious as the sine and cos ones. Then these would be negative 2. You've got more than one graph on an axis, guys. You should really label them on the equation. No, that's all one graph. Right, so try to answer those questions underneath. So this is a bit of a weird one. So on F, you had the point. On the blue graph, what went with 45? 1. But on the green graph, what went with 45? 2. So basically, okay, I don't really like this. I would never really ask you this. It gets a little bit kind of steeper initially, okay, when the A is bigger, but I wouldn't ask you that question. Just look what's going on with 45 degrees. How's a Pomodoro go? Yeah, great. So let's finish the page. So guys, you can't talk about a tan graph having an amplitude. Okay, tan graphs don't have an amplitude. Only sine and cos graphs have an amplitude. Okay, but so quickly try answer B and C. Yes. In the holidays, what time do you sleep to in the morning? In the holidays, do you know what time do you sleep to? Do you read?
Oh, it's nice of them. Oh, I wake up at like 2.
In the afternoon?
Or like 3, depending.
I think I've slept past half of eight for like 30 years. Okay, right.
Wait, so just like quite a couple of days.
I said, I don't think I've slept past half past 8 in the morning.
Oh, but you and my dad.
In the holidays, I can go to sleep at like 10.
Yeah, normally I wake up at 5. Okay. Still won't get up after. If I sleep past 7 on a weekend, that's really late.
Yeah, me too.
Yeah. Okay. Right. Okay. Right. So quickly. Okay. Okay. Right. Let's go. We're gonna have a break now. So first of all, are those? Listen. So sine and cos graphs change from increasing to decreasing all the time, right? But a tan graph is either the one or the other. In these cases, okay, are they increasing or decreasing? If you're moving from left to right, you'll always, no matter where you land on this graph, if you go from left to right, you'll always be moving uphill, right? So we say that they're strictly increasing functions. Okay. So these increasing. And for all tan graphs, the range is going to be the same thing. Okay. They ask you about the domain. Okay. So the domain will just be what's given. So in this case, it was between 0 and 360, but then you just have to add the asymptotes in. Okay. And you also have to say x cannot be 90 and x cannot be 270. So that is your domain. Yeah. What's that?
The bigger one, 45.
45.1, 45.2.
Oh.
Okay. Right. And what's the range, guys? Okay. What's the smallest y coordinate you can have? There's not a smaller. Okay. It goes down to negative infinity, right? And it goes up to positive infinity. And there's no gaps. There's no horizontal asymptotes, right? So you can either say y is an element of negative infinity to infinity, or you can just say y is an element of reals. What's the what? The infinity is not a number, it's an idea. The range will always be the same for all tan graphs. Yeah, kind of.
Like we have 17 seconds. The rest of it is.
So we want to get some.
Five, 4, 3, 2.
Right. I've got time. I'm going to get the Friday time 6 minutes from now. Right.
So do you want to tell us what this minutes? So that's
Hey, right away. That's fast.
What's the difference?
We actually talked 2 minutes.
No.
So what's the difference? Dogs in America. Dogs in America love canine. And dogs in America. Okay, why? Let's go. It's not bad. So bad. Like, no, I told you, don't tell anyone, Robert, because I showed it to him first. I was like, it's been fun. Because he told me to find history jokes, and I'm doing America and China. I had another one as well. I'll tell you about that. Wait,
A long week.
It's just very funny.
Eating a toffee. Ah, kamu.
Come, let's change champion.
Kamu, a champion one.
Let's change with top down ones. You like champion. You like the champion. So like, don't listen to people. No, you must have them and then they're nice. Yes, but still, you know, it doesn't get better.
Amplitude is so much.
I don't want to get into this. We have something we didn't start from. No, we're doing the. That activity. Downstairs.
Siempre te la. Isn't it boyfriend on me? He's like, oh. Because of a boyfriend sleep. But actually, also, Legal looks is not supposed to be the one this one is blocked, but like that's getting close. And like I'm actually not saying this. This is these things like so he's like so talks about boys. That just sounds cool because it was I just don't know how
Yes, I was like, mga that means today that we was interacting with games as well. How many messages are they like?
The use of punctuation to.
these niggas are funny.
Stuff that we added.
There is.
Yeah, I'm just saying, right, you took it.
So sure. Okay.
Oh, nice, fancy. He's thinking he's marrying one of the other.
Oh, yeah,
It's not, it's been very wide.
That's
The other one could just marry one of them. So he said it's not just the actual. Actually, yeah, that's the business I used to be. And so Damon marries, so now they all married, right?
Yeah.
It's the next night. So the Lord of the time. Oh, yeah, sorry. Yeah. Yeah.
It's like,
Yeah.
it's like you're writing from the inside.
Yeah, yeah. So it was like, so it's BBC added one. Still my that was just a request to social the baby that Linnea gives birth to on the day. So Linnea chooses for everyone else to be and she walks all the way to the he's like, I will make up the parcel upstairs, and it was just like staring at us. So we took it. Everyone just like,
so small.
she's like, no. Anyway,
It's like there's no.
so it's one of those bad.
Like,
I think I speak that part excellently. Yeah. But it's so sad. I've seen
Ah, that's
it and she's
Timing is.
the book is 170 years. Is. It's also Japanese.
I don't know why.
That's the biggest one in Amazon.
You just started like making one of those flipping things that they put on your goggles. Like,
The Japanese.
it's like to help you like
That's actually all.
even out your kicking or something and make it good. And I had a flipping headache off that.
What?
My brain. It's not my brain too much. No, it was like something. You said it was making like things that had to.
I'm not having kids.
I don't know.
No, Sybil, don't say that.
I don't even remember.
Don't take one for the team.
I don't remember.
No, it's a yellow. It's like a machine that goes like checking anything or like goes up and you still would have eaten. No, you don't. So now ask Jamie to take it to the
Right, thank you guys, please.
Name one superhero that can be no one is that.
Right, let's go. Right, there we go. Right, let's go, please. Okay, so now, guys, okay, if I gave you a parabola and I said to you, y any graph in the world doesn't have to be parameter, right? Okay, be any function, and I say to you y, no, go to the top. Y is equal to x squared, right? Okay. Then, if I go and reflect that, Taylor, about the x-axis. Taylor, when I reflect a point about the x-axis, what coordinate changes signs? The y, right? So any graph in the world, same thing happens to an equation. So if I reflect it about the x-axis, it'll become negative y is equal to x squared, and you end up with y is equal to negative x squared, right? So to reflect any curve function about the y, about the x-axis, you change the sign of every y into negative y, and then make y the subject of the formula. Okay. So remember, x squared looked like this, okay, and negative x squared was just the perfect reflection about the x-axis. So now, okay, if I take the equation of h, okay, where h is a reflection of f of x is equal to 2 sine x about the x-axis, go tell me what that equation is going to be. What h of x is going to end up being equal? So if you don't have to show any steps, but if you want to go through the steps, f is the graph, y is equal to 2 sine x. So if I reflected about the x-axis, what's it going to become, Nikita? Negative y is 2 sine x. You can skip out all of these steps. Okay. And you end up with y is equal to, I will not go through all of this personally. Okay. But your final answer, they said you must call this new graph h. That's its name, right? Okay. So you get h of x is equal to negative 2 sine x. Okay, so if you're sketching that from scratch, okay, you just enter into your calculator. But I want you to take a few points. Now I want you to sketch h on that same set of axes. So what do we simply do? Pick your significant points. So what's 91 going to become? What's 270 negative 1 going to become? If you reflected about the x-axis. So without using a calculator, go draw that graph. 92, sorry. Does it look like negative 21?
Yeah.
Look at the graph. Negative 2.
It is one next to it.
Okay, so all I do, the points on the x-axis will stay the same. You fold over the fold line, they stay on the fold line. Kavish? Okay, so
I knew it.
Therefore, sorry. 92 for Friday, okay? 92 is going to become what? A fold 90 negative 2. And 270 negative 2 is going to become? Yes. Right. So your graph is a perfect reflection. So guys, when you get a negative number in front on a sine graph, it's going to start with a negative gradient from naught. When you get a positive number in front, it's going to start with a positive gradient. Okay. Right. Come, keep going on the notes, guys. Are you being a pants?
Old fractures.
I'm pulling you.
Hey, I said.
Right. I'm pulling second now. Yay, the behind.
I never said it's not that.
Right, and for that, I'm going to have to take away a piece of the bottom.
Yeah, thanks.
Me, I don't think you can speak bullying.
Okay, give me there.
I don't know how to say. Yes, lots. Okay, right. So, right, Robin, what's this equation going to be? If Q is tan X, what's going to be the equation of the reflection about the x-axis, Robin? Good. Okay. Right. But then you're going to go draw that graph below on the next page, in other words. Right, so there, guys, there's a graph of tan x. Okay, just draw in your asymptotes, please. That'll be x is equal to 90. And that'll be x is equal to 270. Right, now you're going to take this graph over here is, what was it? P of x is equal to tan x, the red one. Right, they want you to go draw q of x is equal to negative tan x, which is just a reflection of the original graph about the x-axis. So what's the important point on a tan graph? 45, right? So on the original graph, you would have labeled 45 1. So you must label that on the reflection as well. Right, so try to reflect that graph about the x-axis. Got to calculate it first. No, all you do is this. So let's do it together. Okay. The original point was 0, 0. Will that change if I fold it over the x-axis? No. So on the fold line. 45 1 will become. So let's label that 45 negative 1. Okay. $45 negative 1, right? So your first part of the graph looks like this. Right? Then remember, here on the original graph went 135 negative 1, what's that going to become? Good. This is going to stay the same. This was 225 1, it's going to become 225 negative 1, right?
Oh no, see, I did the little part right.
Okay. So again, just like with the sine and cos graph, if the number in front is positive, it starts with a positive gradient. If it's negative, it starts with a negative gradient. It's the same thing with tan graphs. Okay, this was the graph of tan x. What is it? Tan x, yeah. And this is the graph of negative tan x. Okay, so if the number in front is positive, starts with the positive gradient. Number in front negatives. Okay. Right, and then the last bit is going to be over here. Okay, and the asymptotes are the same. Right, okay, so now, okay. So, what is the period of graph? Okay, the period of trig graph. Waiting. Okay, what do you understand by? Read it for me then. Okay, again, what does it say? No, yeah, carry on.
The period changes of a trig graph is the number of degrees it takes for the graph to complete.
Okay, so the period of a graph, okay, is the time it takes to complete the full wave. Laura, come on. Okay, so how do I see the period of a graph from the graph? So let's take a look at this original red graph. Okay, so this is the graph in red, is the graph of y is equal to sine x. You highlight them in the same colors. Yeah, no, in different colors. Okay, right, so y is equal to sine x is the red one, right? Guys, come on. Okay, then I've got y is equal to 2 sine x, which is. Oh, no. Okay, so no. Yeah. So y is equal to 2 sine x is the blue one. Okay, and y is equal to negative sine x is the purple one. I don't know purple. I'm going to make green. Right, so for all of these graphs, what's different about them? The amplitude is different, right? If you change the number in front, the energy that goes into the wave increases, right? So the amplitudes are all different, okay? Or if they start with a negative case, it's a reflection, right? Okay. So the amplitudes are two of them are the same, but the one starts with a negative gradient. Okay. So yes.
Is that green or what is that?
That's green. Okay. That's negative sine x. So if it's negative, it's a reflection of that graph, right? So it starts with a negative gradient. Okay. They both have an amplitude of 1, sine x and negative sine x. Okay. So what is the period of a graph? It's how long it takes to complete the full wavelength. the period of these graphs, okay, are they different?
Yes. Oh, no, no.
Okay, how long does it take to complete the wavelength? If I use this highlighter here in brown. Okay, listen. Okay, this, is that a full wavelength? No, a full wavelength is it's got to be back, moving in the same direction. It's got to be increasing. So the period of this, it's taking 360 degrees to complete a full wavelength. Okay, that's the graph of sine x. Another way you can tell the period of a graph is you look at the difference between the maximum and the minimum. So if I take this distance, okay, so this graph carries on here. Okay, what's the difference from negative 270 to 90? How far do you travel? From negative 270 to 90. So that's 360. So the period of that graph, sine x is 360, right? Okay. It's a gap between the maximums, the gap between the minimums would also be 360. Okay. If I look at the graph of the blue graph, tell me what the period of that graph is. Also 360, right? The amplitude changed, but the number of waves, okay, in 360 degrees stays the same. It's 1, right? Okay. This graph over here also has a period of 360 degrees. Do you agree? Even though the amplitude is different. Okay. And the graph with a negative gradient starts with a negative gradient, has also got a period of, it's going down. That's not a full wavelength. How long does it take to complete a full wavelength? 360 degrees. So for all of these graphs, the period is 360 degrees. And likewise, for a cos graph, they're also 360. Okay. Right. If I now go to this tan graph, tell me what the period of those graphs are. And guys, we've got 5 minutes. Okay. We'll work out the period of those tan graphs. How long does it take to do a full wave? Okay, so the way I look at it with a tan graph is basically where am I back at naught? So it takes this graph, the period of a graph means how long is it taking to repeat itself? Okay, if I look at the previous one, okay, if I look at, okay, come on. Okay. Right, on the previous graph, okay. So when you think of a period of a graph, how long it takes to repeat? So to get from a maximum to another maximum, how long is it taking? It's taking 360. To get from a minimum to a minimum, it's taking 360, right? So that's another way you can think of it. So if I look at this one, how long is each tan graph taking to get back to 180? It's taking, sorry, to complete the full wavelength. It's every 180. Everything is repeating every 180 degrees. If you look at the gap between the asymptotes, what's the gap between 90 and 270? It's 180. If I look at the gap between 45 degrees, okay, 45 to 225 is 180. This graph, these tan graphs are repeating themselves every 180 degrees. You get a full tan graph between the asymptotes. It takes 180 degrees to complete a full tan graph. You with it? Okay. So the period of a standard sine and cos graph is 360, but the period of a tan graph is 180. So any graph of the form y is equal to tan x is 180. Okay. Nearly there, nearly there. Okay. Right. Everyone got that? Right, now. Okay. If I right, so on this graph over here, okay, we've got this purple graph is cos half x. Okay, all of these graphs have the same ones. So you've got the graph of cos x, okay, which is the one. Let's make it green. Okay, so here's cos x. No, man, I'm speaking nonsense. This is a graph of cos a half x. Okay, Robin. Okay, so that's cos half x in green. Cos 2x is the graph in blue. And cos x is the original red graph. Right. Okay, so if I look at the red graph, okay, the original cos graph, in all of those cases, the number in front hasn't changed. Okay, so the amplitude is all the same. Capish? Let's go. Right, okay. So, come on. Cos x. Okay, what's the period? How long does it take for the red graph to complete the full wavelength? It takes 360, right? It's taking 360 degrees to get back to a maximum. Okay, it's repeating itself every 360. You will see that. So the period of this red graph is 360 degrees. Okay. It's taking 360 degrees to complete a full wavelength. And 360 degrees is, we're going to look for a pattern, is 360 degrees over 1. Okay. Speak to your neighbor. The blue graph, which is a graph of cos 2x. Understand it out? Go tell me what the period of that graph is. How long does it take to get from one maximum to another? Or from one minimum to another? Speak to your neighbor. What's going to be the period of that cos 2x graph? What's the gap here in the blue graph between the maximums? It's repeating itself every
90.
from there to there is
Oh,
what?
180.
Okay, so this graph, the blue graph, is repeating itself every 180. The gap between the maximum and the minimum is 180, right? Okay, so the period of cos 2x is 180 degrees. Okay, which is 360 divided by 2. Right, and for the green graph, for this green graph, the last one, how long does it take to get back to a minimum of -1? How long have you traveled for before you get back to a minimum of -1? Good. It's 360 plus 360, right? Okay, so the period of cos half x is 720. And 720 is the same thing as 360 divided by a half, right? So how does an equation link up to the period of the graph? Well, if I look at what I'm highlighting in yellow here, if there's no number in front of x, what number is there?
1.
Okay, so that's over 1, right? Okay, that number there, over 2. That number here, over a half. Okay, so in general, okay, if you've got a graph cos bx, okay, then the period of the graph is going to be 360 divided by b. You with me? Okay. All right, guys. Well done. Thank you. What, Robert?
Dress up as your favorite Yeah. That's all.
That's quite funny. Come up with an expected plan,
My friend's honey.